In this section, we're going to be looking more deeply into how we can turn a linear transformation into a matrix, or at least use a matrix to represent it. So we're going to go in some detail on how these work. So let me do some examples to illustrate some things to you. When we're in R3, we have three basis vectors. And they usually go by these names. E1, this is the vector 1, 0, 0. E2 is the vector 0, 1, 0. And E3 is the vector 0, 0, 1. Very important because we can actually use these vectors to create any vector in R3 from them. But more about that later. Let me do some other stuff right now. Suppose we have T from R3 into R2 is a linear transformation. And I know, let's say I know this information about it. Suppose I know just this amount of information about the linear transformation. Well, at least I know it's a linear transformation. So determine a formula for T of x, where x, of course, is in R3, which is the domain. So it'd be a general formula that describes T of x for any x that you can feed into it. So let me do something here. T, if I take a general x, let's say, I don't know anything about it, but let's call it x1, x2, x3. I can break this up into the following. So all I did was break up the vector into pieces like that. Next thing I'm going to do is factor out those x's. So you see how I took a general x and I was able to write it as a linear combination of those basis vectors. And since T is a linear combination, or since T is a linear transformation, I can break this up into the following. Now, I do know what each of these is equal to, so let me go ahead and put them, x1 times, now t of 1, 0, 0 was given as 1, 3. And t of 0, 1, 0 was 4, negative 7. Oh, I should probably remind you, that is E1 right there, that is E2 right there, and that is E3, just in case you couldn't remember. So then we move on, x3 times, and t of 0, 0, 1 was equal to negative 5, 4. And so now I can compile it all together. I'll have x1, 3x1, plus 4x2, negative 7x2, plus negative 5x3, 4x3. And finally, I can put it all together as one vector that looks like the following, x1 plus 4x2 minus 5x3. That's the first entry. Second entry, 3x1 minus 7x2 plus 4x3. And that is t of, well, let me go ahead and put it in here. So for a generic x, I now have a formula, and all I needed was two things. I needed to know that it was a linear transformation, and t was, that is, and I needed to know what it did to the basis vectors. Now, we can also go a little further than this. If you look, let me matrixize it. You can try and do the multiplication yourself, but this is what we're going to be working with in this course. In fact, this, and I mean in this section, we're going to be working more with these matrix transformations. This is called the standard matrix for t. Now, last time I made a mention that not every linear transformation was a matrix transformation. However, every linear transformation that we do in this section is going to be, every linear transformation will be a matrix transformation. In fact, for this course, I'm pretty sure just about every linear transformation will be a matrix transformation. Those things that are not are, for the most part, outside of this course, and I'm not sure just yet if I'm going to even divulge what those things are. Now, remember this, I did the following, x1, x2, x3, which is equal to x1, e1, plus x2, e2, plus x3, e3. This is true for any, so I could say this. So for any x in R3, we have, so I can write x as just a general vector, but I can do this. This shows me that this is in the span of E1, E2, and E3. Since that's true for any possible x, this implies that R3 is a subset of that span. Now, on the other hand, R3 does contain it, so we know that R3 contains that span because it contains all of those vectors and certainly contains any linear combination of those vectors. So we can make the equation then R3 is equal to that span. And in general, R to the n will equal the span of E1, E2 up to En. In those cases, we'll change the definition only slightly for the EIs, just so they have more entries so that they can be in different places like R3, R4, all the way up to Rn, whatever that may be. Now, in the previous example, we had T of x was equal to a matrix times the vector x. That was the whole point of what I was doing in there. And in fact, that A was equal to the following: T of E1, T of E2, T of E3. So that T of x equals T of E1, T of E2, T of E3 times x. Here is a theorem. Let T from Rn into Rm be a linear transformation. Let E1 equal, this is where we're going to have, let me make these extended. I'll have a 1 in the first component, then all zeros after that. And then E2 will have a 0 in the first component, but a 1 in the second component, and then zeros thereafter. So if you want a general EI, you'll have zeros, then you'll have a 1, and then zeros thereafter. And of course, that 1 is the ith entry. And then finally, go all the way up to En. Since we're in Rn, we've got n of these things. This is where we have all zeros until we get to the last entry. So those are what we call the elementary vectors, or elementary basis vectors. The word basis will be defined later on, but I'm going to use the phrase now since I probably can't stop myself. Let A be the matrix that equals T of E1, T of E2. Remember, when I write these, each of these T of E's is a vector in Rm, because T's range lies in R to the m. That means we have m rows. And of course, though, we have n columns since the domain is Rn. So anyways, we let A equal this matrix, then T of x equals AX for all x in Rn. And the proof is really simple. It's not much different than what I had. So what we can do is, if x is in Rn, and I should probably use full sentences here because it's a proof. A proof is a formal collection of statements to try to deduce a point. So if x is in Rn, then we can write x equals, and I'll make a vector as small as I can, but enough to show the details. So since x is in Rn, there's n entries for it. And then we can write x equal to, just like I did before, we can do x1 and then have all zeros after it, plus 0x2 and then all zeros after that, all the way until we get to the end where we have zeros until we get to one final xn. And I'm sure you know what I'm going to be doing here. I'm going to factor x1 from the first vector, which leaves 1 with all zeros after it. Instead of writing that vector again, I'll simply do this. And then we have x2 e2 plus dot 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 plus xn en. So that's equal to x. T of x then will equal t of x1 e1 up to xn en. And of course we can break this up. x1 t of e1 plus dot 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 plus xn t of en. And then I can just simply disassemble this into a matrix matrix times a vector. So that works out TE1 up to TEN times the vector x. Some notes. These are some notations you'll experience as you read through whatever section that this happens to occur in. It's almost like we can't stop these things from coming, even if I want to hold off on them till later on. So let's write r to the n. We know this. You can prove it if you'd like. I did it for R3. You can see that it's true here. It's pretty simple. So there's one thing. Plus, this thing here called I sub n is equal to the matrix whose columns are those e's. This is the n by n. The reason why it's n by n is because there's n columns. You can see that. But now each of those is from Rn, so the number of entries is n as well. So this is the n by n identity matrix. If you want a visual on it, it looks like this. We'll have basically ones down a diagonal, like so, but everything else will be 0. And so sometimes you'll even see this. You may see the book do something, they may do something like this. And they'll just put big giant zeros here to indicate that on the main diagonal, they call it, the diagonal there, you have all ones, but anything off of the main diagonal is 0. Of course, what happens, the reason they call it an identity matrix is if I take a matrix that's compatible with multiplying by it, then the identity matrix will leave that matrix alone. It won't do anything. So it's really a multiplicative identity, if you will. This is, in this world, in the world of matrices, this thing here is like the number 1. As an example, let T from R2 to R2 be the transformation. So I'm not saying it's a linear transformation. Let it be the transformation that rotates each point in R2 an angle theta about the origin. And I should say this is counterclockwise. The way we normally do angle measurements in the plane is in a counterclockwise direction. So I want to find a formula for t of x. All right, first, let me give you an idea of what's going on here. Take any point, I don't care what it is, x, y, and draw a line connecting here. Now what I'm going to do is rotate the plane by an angle of theta, like so. Then this point will follow the rotation until I guess it gets to around here. Let's call that x prime, y prime. That's a new point. And so we want a formula for the function that does that. And the key to it is this. We know that R2 equals the span of E1 and E2. And if you need recollection of what that is, E1 is the vector 1, 0. E2 is the vector 0, 1. Now basically the way this works is if I can figure out what the function does to these, then I'll know what it does for any point. So all I got to do is follow those two things. So let's go ahead and take a look at how that looks on the graph. Let's start with 1, 0. Let me put it here. And so there is E1, it's at the point here. And then I'm going to rotate it an angle, I don't know, let's call it theta. What point does that end up at? Well, the interesting thing that you should know is the length of that vector is 1. So as it rotates, the tip of the vector is on a circle of radius 1, which means we know that any point on a circle of radius 1 looks like this. So I know what happens to 1, 0. Easy enough. Now let me draw another picture. So what this tells me, let me do that. T of 1, 0 equals cosine theta, sine theta. Now let's take a look at another one here. Let me draw, I want to make it big enough to be able to be seen. So let's put right here 0, 1. See if I can vectorize it. Now it's also going to do the same thing. I'm not exactly sure how much theta looked like. I'll try to. It didn't quite go 90 degrees in my picture, so it's going to come here perhaps. I have a little theta there. Unfortunately, that little theta is not the whole angle. So the whole angle, we have 90 degrees here. So the whole angle from start to finish, if you will, is theta plus 90 degrees. So this point here is cosine of theta plus 90 degrees, sine of theta plus 90 degrees. So T, it's a terrible looking picture, but hopefully you understood it as I was saying it. T of 0, 1 equals cosine of theta plus 90 degrees, sine of theta plus 90 degrees, or pi over 2, whatever version you want to use for it. I want to clean up a little bit. Remember this. Cosine of theta plus 90 degrees equals cosine of theta times cosine of 90 degrees minus sine of theta times sine of 90 degrees. These are the sum of angles formulas for the trig functions. Well, cosine of 90 degrees is 0. Sine of 90 degrees is 1. So this ends up being negative sine theta. And then sine of theta plus 90 degrees equals sine of theta cosine of 90 degrees plus sine of 90 degrees cosine of theta. And as before, the cosine of 90 degrees is 0, sine of 90 degrees is 1. We just get cosine of theta. So I'm able to simplify it a little bit. So t of 0, 1 equals negative sine theta cosine theta. And there we have it. So my formula looks like the following. T of x equals, let me go ahead and put in my t of 1, 0. I think I shortchanged myself on this. I think what I'll do first, before I do that, let me do t of 1, 0 to remind you what the standard matrix is. I'm currently writing the standard matrix as I speak. And then let me go ahead and put those in. We know that this was cosine theta, sine theta. Then we had negative sine theta, cosine theta. So that is what they were asking us for. That was the formula that they were instructing us to try to get. To illustrate this last one, I'm going to do a simple numerical example. Let t from r squared into r squared be a linear transformation that rotates points about the origin negative pi over 4 radians. Of course, that means we're going to go clockwise because negative works clockwise, positive works counterclockwise. Find the standard matrix for t. So, well, we know what it is. T of x equals cosine theta, sine theta, negative sine theta, cosine theta, times x. So this guy right here is our standard matrix. And let's go ahead and put in our numbers then. If theta equals negative pi over 4, the standard matrix is then this: cosine of negative pi over 4, sine of negative pi over 4, negative sine negative pi over 4, cosine negative pi over 4. And I don't care if you remember these or use your calculators for them, but I'm going to give the exact answers to these. Cosine of negative pi over 4 is the same as cosine of pi over 4. That's radical 2 over 2, or what is a little bit easier to me, 1 over radical 2. Of course, sine of negative pi over 4 is the negative of sine of pi over 4, so I get a negative 1 over radical 2 here. And then I'll just go ahead and complete the rest of these numbers. And it's a clumsy matrix to write, so it might be easier to do it this way. Factor out that radical 2 from every entry. And there it is, your standard matrix. Let's test it. So what I want to do is let's pick a point. So I'm going to pick up a specific point and see if it rotates to where I think it should be. Well, the most natural point to see is I want to see if this point here, let's call it 1 over radical 2, comma 1 over radical 2. So this angle is at pi over 4. That's why I'm choosing it. So there's my point. It's a point on the unit circle. What should happen to that point if I'm rotating negative pi over 4, so if I'm going negative pi over 4 in that direction, that point I should have 1 over radical 2, 1 over radical 2, should go back to the x-axis and give us 1, 0. Let's see if that is in fact what happens. So then my t of 1 over radical 2 times 1 over radical 2. I'm just doing this to check to see if I did everything right. Well, let me go ahead and put in my standard matrix. And then let me go ahead and put in my vector. One thing I can do is I can take this scalar, this 1 over radical 2, and actually multiply it through to the vector. There was a thing that we did that said we were allowed to take scalars or real numbers and pull them into and outside of matrix multiplications like this. So if I take this 1 over radical 2 and multiply it to that, this is what I get. And now let me go ahead and do the multiplication. I'll use the row vector method for doing it. And I'll keep doing it for a while to remind you of how it works. But you match this row with this vector, of course. And so I take 1 times 1 plus 1 times 1. And same thing over here. Negative 1 times 1 plus 1 times 1. And I made a mistake here. When I multiplied that through, that didn't clean up. The radical 2 was beneath it. This is actually 1/2. My bad. All right, so that means that I have to make these into halves. Luckily, I can fix that fairly easily. And let's see what we get then. 1/2 plus 1/2 is indeed 1, like I wanted. Negative 1/2 plus 1/2 is 0. And so it checks out, so I feel pretty good about my answer. Let me do another one of these geometric transformations to show you how it goes, and then I'll leave the rest of them to you, whatever ones you should encounter in the homework problems. By the way, we do know that the rotation that I did in the last example was a linear transformation, since we could write it as a matrix transformation. Remember, matrix transformations are linear transformations. So in this one, I want to find the standard matrix in R2 of a reflection through the origin So what happens here? If I go and I take a point xy to reflect through the origin means that it's going to give us, it's going to lie on a line through the origin, but it's going to be the exact same point, just like a mirror through the origin. However, over there, we're going to get negative x, negative y. So that's what it's going to do to every point. It's going to reflect it through the origin. So I want the standard matrix for that. And so we need only see what happens to E1, that was 1, 0, and E2, which was 0, 1. We only need to see what happens to those two vectors. So let's start with E1. Once again, I'll put my point 1, 0. Put a little arrow here to vectorize it. Anyways, as it goes through the origin, think about what happens if this point stays on a line from it to the origin, then continues to the other side. It's going to end up at negative 1, 0. So this point here, it didn't go in that direction. It went through and went to negative 1, 0. Similarly, let's take a look at 0, 1. Follow it. Follow the point here. It's got to go to the origin and then continue through to the exact same distance on the other side. What point does it end up at? It ends up at 0, negative 1. So that point there comes and goes to there. So we can see that t of E1 equals negative 1, 0. T of E2 equals 0, negative 1. So then my formula goes like this. T of x equals, I put in my E1 stuff, and then I put in my E2 stuff, and then I attach my x. Let's test. T of x is equal to let's go ahead and multiply it out. Negative 1 times x1 plus 0 times x2 will just be negative x1. Similarly, 0 times x1 minus 1 times x2. And sure enough, it most definitely checks out. Inevitably, whatever book we're using at the time of this class, they'll have other transformations that you can take a look at. I'll leave them to you. Basically, follow the basis vectors and you can't go wrong. Now, what about combination transformations? So let's find in R2. We use R2 because for most people that's where they can see things being rotated or reflected and things like that fairly easily. We have the same notions in higher dimensions, but of course they're much more difficult to graph and so wouldn't be as useful from an education standpoint. But rest assured, the same ideas work in the higher dimensions. So anyways, I want to find in R2 the standard matrix for the combination, and what we'll do is first we will reflect about the y-axis. And then second, we will rotate pi over 2 radians about the origin. And you know that this means counterclockwise. It's just the way we work. So once again, let's go ahead and take a look at what happens to the basis vectors. So we'll start with 1, 0 and see what happens to it. First, we reflect about the y-axis. So we are going to end up here. That was after the reflection. And I think to make this probably that was the first one. I think I'll save myself the effort here. Then we rotated pi over 2. So then we took this thing and then we rotated it pi over 2, which means we're going to end up on the y-axis now. And we will end up at 0, -1. So t of 1, 0 equals 0, -1. Now let's take a look at what happens to 0, 1. So we're starting here. First step is to reflect about the y-axis. Well, if you reflect about the y-axis, that point stays where it's at. So nothing happens during the first part. It's only during the second part that we're going to rotate pi over 2, and that's going to end up at -1, 0. So we only had the second one is the only one that had an effect. And so t of 0, 1 equals -1, 0. So my standard matrix then equals, let's see, for my first column, this is it right here, 0, -1. And then for my second column, I have -1, 0. Another example. Let t from R2 into R2 be a linear transformation. And let the standard matrix so let's just call them these two things, A1 and A2. Don't know what they are, but I'm going to show you a picture of them is what I'm going to do. And so what we have here, just a rough sketch, looks like the following. I'm going to put A2 will be the vector here. So we will call that A2. And then A1 points down this way. Of course, you don't have to be exact, but you should at least have a reasonable sketch when you do these things. What I want to do is sketch a graph of t of -1, 3. And so for my solution, I have t -1, 3 equals, I'm going to do this fast, so let's see if you can keep up with me, t of -1 times 1, 0. I guess fast for me really isn't that fast, but plus 3 times 0, 1. And so that is negative t of 1, 0 plus 3 times t of 0, 1. which of course equals t of 1, 0, t of 0, 1. Let me do this. This is a matrix now is what I'm doing. These are columns, right? And that, of course, is times -1, 3. And so this is A1, A2, times -1, 3. And the way we multiply this out is that we have -A1. I'm sort of being redundant, but 3A2. So let's go ahead and get a picture. What I'm going to do is copy that picture down below, and then we'll work on it. All right, so let's take a look and see what happens. Let's first start with -A1. I'm going to put it back this way. I'm going to try to make it just as long. That'll be -A1. So I've got that. And then 3A2 will be 3 times as long as that. So let's say that this is 3A2, and then see if I can draw this long enough to connect to that point. Close enough for me. Now then, when I go to draw their picture, so let me go ahead and make this a solid line. So then when I go to get a picture, I'm going to do the parallelogram rule, and I'm going to run into my own stuff there. So I'm going to take it out, move you out of the way. I only need to go so far with that, and then I need to copy the other one like so. And then our answer then is this one here. And hopefully you can use your imagination and show and think that that's actually touching the corner of that parallelogram. But that is the sum of those two vectors, -A1 plus 3A2. Once again, the whole idea is if you know what happens to the basis vectors, you know what happens to anything. Another example. Suppose t from R4 into just R is given by t of x1, x2, x3, x4 equals 2x1 plus 3x2 minus 4x4. Show that t is a linear transformation by finding the standard matrix for t. So once again, we look at t of E1. That's the same as t, and so we have 4 entries this time. 1, 0, 0, 0. And let me use my formula. Here, x1 is 1, but I have zeros for x2 and x4. So I have 2 times 1 plus 3 times 0 minus 4 times 0. And that equals 2. T of E2 equals T of, this time we're going to have a 1 in the second spot. And so x1 is 0 this time, so we have 2 times 0 plus 3 times 1 minus 4 times 0, and that's equal to 3. And then we have T of E3 This time we have a 1 in the third spot. And my formula, if you look, there's no x3 here. That means I can only plug in what they give me here. So I'll get 2 times 0 minus, or plus 3 times 0 minus 4 times 0 is 0. And then t of e4, that's our last one. That's t of all zeros except a 1 into the last spot. And the first entry is 0, the second entry is 0, but the fourth entry was 1. And so for that one we get -4. And so this may seem like a bit strange, but my standard matrix is just this. If you want to think of it this way, each of these answers are vectors, but they only have one entry. So my matrix is going to look kind of funny. I'll have a 2 for my first column, then I'll have a 3 for my second column, a 0 for my third column, and a -4 for my fourth column. Very strange looking matrix, but a matrix it is. Next, I want to move on to a definition. A mapping, just another word for a function, T from Rn into Rm is onto if for every B in Rm there exists X in Rn such that T of X equals B. So any vector that I can pull in Rm, T of X will have an X that will map to it. And let me use the last example to show you that that thing was an onto mapping. So the last one we had was T from R4 into R, given by, I'll cut to the chase, it was T of x1, x2, x3, x4 was equal to 2x1 plus 3x2 minus 4x4. This mapping is onto. How do I know? Let x be any real number. Then T, the following vector, will map to that number. If I put in the first slot x over 2 and zero out everything else, and since x3 in the definition is not even listed, I could actually put anything I'd want in there, but I really don't care. According to the rule then, this is twice the first entry plus 3 times the second entry minus 4 times the fourth entry. And that equals x. Since x was picked arbitrarily, I'm able to find something that maps onto it. You can try some other things for some practice, like you could have, if you pick any x in R, in just R, if you pick any x in R, then you could have put x over 3 in the second spot and zeros everywhere else, and that would have also worked.